Hi class, this is Dr. O'Connor, and in this video we're going to talk about energy. And energy is the capacity to do work. We're going to talk about a specific kind of energy in this video, and that is heat energy or thermal energy. So thermal energy and heat energy are the same thing. And later, we'll talk about energy in a lot more detail when we get to another chapter. So for now, we'll talk about heat energy and we'll talk about the transfer of this heat energy. That's the easiest to understand. So we defined energy as the capacity to do work. Temperature, on the other hand, is the measure of the amount of heat energy that's in an object. So we take the temperature, and what we're actually doing is measuring the heat energy in that object. Okay, but we'll talk more about temperature and heat a little bit later. Let's take a look at some units of energy, and the SI unit is called the joule, and it's represented with a capital J. The metric unit is the calorie, and that is represented as lowercase cal. And we're all familiar with calories. So a calorie, and actually I'm going to cross this out because this should be a lowercase c. And I'll tell you why in a minute because it is important. So we define a calorie as the amount of heat required to raise the temperature of 1 gram of water by 1 degree Celsius. And here we can convert between calories and joules. So 1 calorie is equal to 4.184 joules. And we have this equivalence here, so that means that we can form two conversion factors from an equivalence. So here we have 4.184 joules and per 1 calorie. So these are two conversion factors that we derive from one equivalence. So you need to know this. Now, if we have 1,000 calories, that's going to be a kilocalorie. And a kilocalorie is equivalent to 4.184 kilojoules, and that's because 1,000 joules is equal to a kilojoule. Okay, so practice some of these problems and get used to the units. Now, I want to go back about the comment I made here about changing that C to lowercase. Now, we know the 1 calorie is equal to 4.184 joules. And we also know that 1,000 calories is equal to 1 kilocalorie. Okay? But, let me go down here. We also have this 1, and this is a capital C. So 1 capital CAL. This is a food calorie. And this is equal to 1,000 calories or 1 kilocalorie. Those labels that tell you how many calories are in a serving of food, those are actually kilocalories. So for example, a candy bar that is 240 capital C, calories, is actually 240,000 calories. So this would be 240 food calories, which is equivalent to 240,000 calories. That's interesting. Go and get some food item right now and look on the label, and you will see that calories are written with a capital C, and that corresponds to a food calorie, which is equal to 1,000 calories or a kilocalorie. So I thought that was an interesting piece of information. So let's go back here. We can talk about food calories all day, but let's go to this page here. So our goal here is to be able to determine how much heat is transferred when a substance is heated or when it's cooled. Obviously, when you heat up a substance, then that substance is going to absorb that heat. Think about when we put a pan of water on the stove to boil. So we have to turn the heat up. So it takes a little while for that water to boil because it has to absorb a lot of heat before it can boil. We'll talk about why it boils in a later chapter. Now, let's say I run a bath and I have a nice hot bath. I run that hot bath and all of a sudden somebody calls me and I'm on the phone for 2 hours. What happens? I go to my bath and it is cooled. So that water loses heat energy. Okay, so what we're going to look at is, again, the transfer of that heat energy. And in order to do that, we have to define something called specific heat capacity. In your book, they call it specific heat. In other texts, they call it specific heat capacity. And that is represented with a lowercase c. And this is the amount of heat needed. Heat is represented by a lowercase q. So the specific heat capacity is the amount of heat needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. So let's take a look at this list here. Okay, this lists some of the substances and their specific heats. All substances have a characteristic specific heat. Okay, so let's take a look at ethanol here. And here we see it has a specific heat of 0.59. By the way, the units of specific heat are calories per gram degree Celsius. Other units for specific heat are joules per gram per degree Celsius. Okay, you can have it either way, in joules or in calories. Here we have 0.59 for ethanol. What that means is that it is going to take 0.59 calories to raise the temperature of 1 gram of ethanol by 1 degree Celsius. Here we have a specific heat for gold, one for iron, one for mercury. Notice that water has the highest specific heat of these substances listed here. In other words, it is going to take a lot more heat energy to raise the temperature of 1 gram of water by 1 degree Celsius. Let's compare the specific heats for ethanol and water. So we see for ethanol, it's 0.59. So that means that if I had some ethanol in a pan and some water in a pan or a beaker, and I heat those up, I'm going to be able to heat the same amount of ethanol much quicker than the water. That's because it's going to take a lot more heat energy to heat that water than it does the ethanol. So what we're able to do here is use the specific heat of a substance and the temperatures. In other words, if you're heating something, you're going to heat it from temperature A up to temperature B. We're able to determine a temperature change. So if we know the temperature change, the specific heat of the substance, and the mass of the substance, we can determine how much heat is transferred. When I say transferred, what I mean is when I heat up a substance, heat is going to be absorbed by that substance. If I let a substance cool, heat is going to be released by that substance. So let's go ahead and take a look at this equation. The heat transferred, and again, heat is lowercase q, is going to be equal to the mass of the substance multiplied by the temperature change multiplied by the specific heat. And the specific heat we can look up for each substance. Another way to represent that equation is this. Q is equal to the mass times delta T times C. Now, anytime you see that delta symbol, it means a change. The change then here is temperature change is equal to the final temperature minus the initial temperature. So, for example, if I have water at 22 degrees Celsius and I heat it up to 45 degrees Celsius, the temperature change is going to be equal to the final temperature, which is 45 degrees Celsius in this case, minus the initial temperature, which was 22 degrees Celsius. 45 minus 22 gives us a delta T of 23 degrees Celsius. Now, what if I have water that is at 98 degrees Celsius and it's cooled to 22 degrees Celsius? We have water at 98 degrees Celsius and it's cooled to 22 degrees Celsius. Delta T in this case would be equal to the final temperature, which is 22 degrees Celsius, minus 98 degrees Celsius. Okay? Now you can see that's going to give a negative value. And if we plug that into this equation here, Q is going to be negative. Now, let me tell you, there is no such thing as negative energy. What the sign means is, when we see a negative Q, that means heat is released. So in other words, as that water cools down, that heat energy is released. And a positive Q means that a substance has been heated and that substance has absorbed heat. So again, there's no such thing as a negative energy. The signs are just used to show whether heat was absorbed or released. So let's do a couple of problems. All right, where is my first one? Here it is. So problem, how much energy in both calories and joules is required to heat a 456 gram piece of copper from 22 degrees to 287 degrees Celsius? And here we're given the specific heat capacity of copper. So remember, Q, that's the heat energy, is equal to the mass times the specific heat times delta T. We have the mass. Remember, mass must be in grams. So we have the mass, which is 456 grams. We have the specific heat, which is here. We have delta T, which would be delta T is equal to, we want the final temperature, so it's heated to 287 degrees Celsius, and subtract from that the initial temperature of 22 degrees Celsius. So delta T is equal to 265 Celsius units. Okay, so let's go ahead and just plug everything into our equation. Q is equal to the mass, 456 grams, times the specific heat capacity, 0.385. This is in joules per gram degrees Celsius. And multiply that by delta T. And let's see what we get here. So 465 times 0.385 times 265. I get 47,442 joules. So in order to heat up 456 grams of copper from 22 degrees to 287 degrees Celsius, I would need 47,442 joules. Usually the heat is converted to kilojoules. So in kilojoules, that'd be 47.4 kilojoules. But what we're going to do is we're going to fix these significant figures here. We can only have 3. So what we have is 4.74 times 10, 1, 2, 3, 4, times 10 to the 4th joules. Now they also want this in calories. There are 2 ways you could do that. You could go ahead and convert the joules to calories here, or just convert the answer to calories. So we have 4.74 times 10 to the 4 joules. And we know that there are 4.184 joules per calorie. And that would be 11,339 calories. And we need to get the proper number of sig figs. 1.13 times 10. Remember, 1, 2, 3, 4, 10 to the 4th calories. So we did this in both joules and calories. Let's do another one. Here we're asked how much heat and calories is transferred when 90.2 kilograms of water is cooled from 37 to 21.4 degrees Celsius. The heat capacity of water is, and they want this in calories, so we can go to our chart to look up the heat capacity of water in calories, and that is 1, and that's calorie per gram degrees Celsius. Okay, and now we need delta T, and that's going to be the final temperature. And remember, we're cooling in this case, so that's 21.4 degrees Celsius minus the initial temperature, which was 37 degrees Celsius. So we have 21.4 minus 37. Whoops. That's negative 15.6. What we have is Q is equal to the mass, so that's 90.2 kilograms of water. Now we need to be in grams, okay? So let's go ahead and convert that kilograms into grams. So what we have is, we have 90.2 kilograms, and we know that 1 kilogram is 1,000 grams. So this is going to give us 90,200 grams. So let's put that in. So we have 90,200 grams times the heat capacity, which is 1 calorie per gram degrees Celsius, times delta T, which is a negative 15.6. Okay, so let's see here. Remember, that's a temperature change. That's not a temperature. It is a temperature change. It's the number of units that temperature has changed. So we have 90,200 times 1 times a negative 15.6. And I get a negative 1407120 calories. Again, the negative sign just shows us that the substance was cooled down. So in other words, heat was released. So let's go ahead and fix this as far as significant figures. We can only have 3. So what we have is 1.41 times 10. Here we have 1, 2, 3, 4, 5, 6. 10 to the 6 calories. In this next problem, we're being asked for the specific heat of a liquid substance if it takes 636 calories to raise the temperature of a 325 gram sample from 26.9 to 86.2 degrees Celsius. It also asks us to use table 110 to identify the substance. So what we have is our equation, of course. We have the heat is equal to the mass times the specific heat times delta T. So let's go ahead and solve this for the specific heat capacity. So the specific heat capacity will be equal to Q divided by the mass times delta T. So we already have Q, which is this. We have the mass, and delta T will be 86.2 degrees Celsius minus 26.9, and that is going to give us 86.2, 26.9, and we get a delta T of 59.3 degrees Celsius. So now we can plug everything in. C is equal to Q, which is 636 calories, divided by 325 times delta T, which is 59.3. And let's see, this works out to be 0.033, and here our units are calories per gram degrees Celsius. So we can also use this equation to find the specific heat capacity for a substance. We can also use it to find final and initial temperatures if we're asked that. But let's go ahead and look at the table and see what this corresponds to. Let's go back up here to the table. So we had a specific heat capacity of 0.033, and that was in calories per gram degrees Celsius. Well, here I see that gold has a specific heat capacity of 0.031, and mercury has a specific heat capacity of 0.033. They're pretty close there. But I know for a fact that it is mercury, and that's because if you look at the original problem, let's see what we have here. If we look at the wording of the problem, we're told that the substance is a liquid. And we know that mercury is a liquid. Even though it's a metal, it's a liquid at standard temperatures and pressures. So I would say the identity would be mercury. So we can do tests like this in the lab if we have an unknown substance. And we could use the method and compare the specific heat capacity that we determine experimentally to the actual specific heat capacity. And that could help us identify a substance. Of course, we'd be using other methods of identity as well, but when you put them all together, we have more confidence in the identity of our substance. So everyone have a nice day. If you have any questions on the material from this section or any other section, please let me know.